All right, so let's work through this TBIL activity, not in the way they set out, but sort of in I don't know, the way I would have approached it if somebody had told me to, given these two linear transformations, go find S composed of T, right? Go figure out what that is. And we know that that just means we're going to be doing these two linear transformations sort of in a row, right? We're going to start by taking some vector that's in our domain for T, mapping it using T, getting something in my codomain, right? So we're in R2, but R3, and now we'll be in, hold on, I can make it pretty. Finding something in our codomain, and then using that new vector from our codomain, mapping with S to S's codomain, which is R4. So that's sort of the process that we're going to go through. I'm going to go ahead, right, the first question they actually asked in TBL was, if you've done all of this, what is the domain and codomain for this composition? And so we just found that. We might as well go ahead and answer that question. We can map from R3 to R4 as our codomain, but let's approach this just sort of, I don't know, dumbly. So first we need to deal with T. So we're going to take some vector from R3. Let's just go ahead, X, Y, Z. Let's go ahead and figure out what that is. For this one, we're using our standard matrix B. Eek, I need more space than I gave myself. Hold on. So if I want to deal with that one, -3, 5, -3, 4, I'm going to have that with our X, Y, and Z. Right? We can either do that matrix multiplication, which we're not supposed to know about super well at this point, but we know matrix multiplication, we're multiplying by a column vector. This is just those linear combinations, so this is going to end up in R2 with 2x plus y minus 3z as our first component, and 5x minus 3y plus 4z as our second component. All right, so here we have our A times our vector. So we now have that transformation. We are now, right, we've mapped, we're in R2, which means that we can move forward through S, right? So if I want to be good about this, I need to do something like S of all this, right? So I'm just actually going to make another line instead of trying to like modify this so my equal signs will work. Let's look at S of T of V. All right, so now I'm going to take A, our matrix A, 1, 0, 3, -1, 2, 1, 5, -2, 2x plus y minus 3z, 5x minus 3y plus 4z. Oof, she nasty, but it's going to be okay. I'm trying to think how we could do this nicely. Now I see why they wanted us to go through the basis vectors. I'm having some regrets, but it's fine. I'm going to go ahead, since we do know matrix multiplication, I'm going to go ahead and just do that matrix multiplication to find our new vector in R4. So, oof, gross. I'm going to need one of the first element. I need to just write this in the middle. It's like there's 3 terms in that element, so my part of me wants to just treat you those separately, but I'm going to go ahead. I got it. So this will be 2x plus y minus 3z, and then plus 10x minus 6y plus 8z, right? 2 times that second component. Really need larger brackets on all this. All right, and then we move down to the next one. I don't need any of the first one. I only need the second. Oh, that's lovely. Thank you so much for that. Okay, 3 of the first, 6x plus 3y minus 9z, 5 of the second plus 25x minus 15y plus 20z, and then a -1 and -2. Cute. All right, let me go ahead and clean that all up. by combining like terms for each of those elements. I probably need that to be a little larger. Looks like we have 12x minus 5y plus 5z, and we have, oh, that's easy, I don't know why I'm pausing, and 31x minus 12y minus 11z, or plus 11z, and the negative 12x plus 5y. I'm already sketched out by this, the first and second, the first and last. I'm like distracted by the fact that I'm like, oh, they're gonna be the same, but different, multiplied through by a 1. Anyways, there we end up. So we have this as our sort of result. So if we did this, we could now be like, okay, well, if I really wanted to, I could go all the way back to this thing and say, okay, I can give you a new standard matrix, right? I could say, instead of doing all of this work, if you want to do this multiple times, let's just define the standard matrix for this composition as 12, 5, 31, negative 12, negative 5, negative 3, negative 12, 5, 5, 4, 11, negative 5. Cute. And it does sort of make sense, right? Let's look back at all the different dimensions of these different matrices. We had a 2 by 4. We had a, I want to change this back to blue, a 3 by 2. When those two things combined, we ended up with where we have last, our C, which is a 3 by 4 matrix. So that's sort of like if I was painstakingly being like, I don't know, let me just put a vector in here, right? We also know that we could move through a basis, which is what TBIL wanted folks to do. So let's just look at what that would look like, right? So we have to realize that, again, if we're talking about this particular composition of transformations, we're starting in R3. So we're going to have our 3 standard basis vectors in R3. Let's see how that would have looked instead. All right, so we would have said, okay, we still need to do T first. Let's start with E1, which is 1, 0, 0. How does that work when we're dealing with that original matrix, right? That standard matrix. Well, that would have just been a 2, 5, right? We can just grab that column of my standard matrix here. And then we go like, okay, well, let's go find what S of T of 1, 0, 0 is, that standard basis vector, which means I need S of this 2, 5. And that's a little bit less hellish to do, right? Because if I'm looking now at my S standard matrix, I know I need, we've done this before, this was, oh gosh, what was it, AT2. We need 2 of the first column, and we need 5 of the second column, which leaves us with 12, 5, 6 plus 15 is 21, and negative 2 plus 10 is 8. These did not work. Something is wrong. So, 25 plus 6 is 31. That helps. And did I screw up here? Oh, it's a negative 2. See? There you go. How am I checking my work? Well, I was just looking at the goal of working with standard basis vectors, right, is that we end up with those columns that we expect to see in our standard matrix. And so I was like, wait a minute, something happened. So this is a lovely way to do this problem that doesn't require so much matrix multiplication and like combining like terms. Pretty classy way to head there, but it's definitely not the way my brain would have started. Like I would have started being like, well, let me just throw X, Y, Z in there because I know how to do that. But this points out sort of why the TBL book, that activity book, wanted us to move through those standard basis vectors, because this was AT2, right? We did this in AT2. And so was this. And so we've got both of those skills down really, really well. It doesn't require us to use the matrix multiplication that maybe we're not super comfy with, to sort of recognize that, oh, cool, there is this lovely thing happening. Now, we know this all leads us to something different. The whole goal here was that we wanted to show that if I did this matrix multiplication, turns out I don't really need the X, Y, Z, all those pieces in there, because it's all going to work out perfectly anyways. 2, -1, 3, 5. Because when we peeled these apart, we ended up with the same thing. All right, so I feel like this is a lie. This is what we needed. Cool, cool. So we're doing our 4 by 2 times our 2 by 3. Okay, so we talked about in class how this works, this matrix multiplication, right? We're going to go ahead and just multiply the row of our first matrix by the column of our second, element by element, adding those products together. So what that looks like for that first element here is that we're going to have 2 times 1 plus 2 times 5. Cute. And then we'd move over. So I'll just go ahead and circle this so we can see where it came from. Let's change our color. If I want to move to the next column, I'm still talking about row 1 here. Nope, don't do that. I'm still talking about my row 1 here, but I multiply it by my second column. That means I'm going to be in row 1, column 2 of my resulting matrix, right? So in this case, 1 times -1 plus 2 times -3, right? And we can already see what's happening here. This is going to do the exact same thing that we saw when we did this sort of step by step. We have a 12 for that first element. We have a 1 minus 3, a -5 for that second. And so this will keep going and we'll end up back with that same standard matrix we found before. The real advantage here now is that we could just do this with technology, right? I could type this into a matrix calculator, into some computational, some sort of software, some, my gosh, processing language would be fine. But yeah, so we could easily have this done for us. So this is our matrix multiplication. This is really the point of this particular unit. They just wanted to sort of, I think, show this from a more geometric standpoint, this idea of these linear transformations and doing them one at a time to arrive at this new standard matrix, as opposed to as an algorithm or procedure for what matrix multiplication is.